The, or,
Yeah, it means yes.
the heart.
The heart, yes.
Heart.
Okay.
Maarten the heart.
Yeah, it's the heart, this type of heart, yes. So,
Fine.
yeah. Almost everybody's there. I'm still waiting for two persons who also said they will be here. There's one. Okay. I'm going to look on, I suppose. Well, from those who haven't seen me in my first presentation, my name is Maarten Hart. I'm from the Netherlands, and I'm going to present about heat that is involved in flood. With the question, is it a problem or is it an answer? Well, just see how this thing works. No, not like this. This button. Oh, it's the arrow. Yes, right. Okay. There are a couple of chapters. Heat in flood models is a problem. How much heat is involved? What does heat do? And a heat model, my own heat model, a conclusion. And if there's some time left, we can pick some out of the rest. And probably we will skip that because of time. First, heat in flood models is a problem. What do I mean? Well, I'm going for two examples. The impact model and the catastrophic plate tectonics model. And the two leading flood models at the time. And all flood models seem to have one problem in common. And that's that there's too much heat involved. The impact model is from Michael Hart, he also showed a book from, and the plate tectonic model is from John Baumgartner. Again, if we look at the moon, this is an exaggerated height map. We see this lot of craters, and we see those craters on Mars. We also have this Vredefort crater on Earth. According to Michael Hart, he extrapolated the amount of craters from the moon to the Earth. He calculated how much craters we should have on Earth. And he says, well, there should have been 36,000 craters with a diameter of 30 kilometers or larger on Earth. Well, that's quite a lot. And critics say, well, such a bombardment would sterilize the planet. Okay. The other model, the catastrophic plate tectonics model, says, well, the Earth looks like this now, it used to look like this before, which would imply that during the flood the continents moved for a couple of thousands of kilometers. And he actually calculated that this is technically possible, given the right conditions, which are rather extreme, but possible. And then the critics say, well, a sudden exposure of the mantle to 70% of Earth's surface would release enough heat to boil the oceans dry several times. So they say that's impossible. Okay, now I'm going to look how much heat actually is involved to see if these critics are right or not. This is a map of the known impact structures on Earth. The Vredefort crater is also there. But
Overall time.
that are the confirmed craters that we have found so far. It's 188, I suppose. Let's take a look at the Chicxulub Yucatan crater in Mexico, which supposedly killed off the dinosaurs. So it's over there. Yeah. Well, during the impact, it probably looked something like this. That's quite massive and impressive, and if you would stand over there somewhere, well, you're gone. This is the actual size of the impact fireball. And when you look at it, but when you zoom out of the Earth, you see it's like this. It's still large, but not killing the entire Earth. You see it over there. Okay, if I take this example, there are a few parameters that work for this particular crater. This is an example of how you could get such a large crater that they found. You can get a block of rock with a diameter of 18 kilometers with a speed of 17 kilometers per second, which is a typical impact speed. Then you are left with a crater of 170 kilometers in diameter. The energy involved is 1.3 times 10 to the 24th power joules. For comparison, the Tsar Bomba was 2.1 times 10 to the 17th joules. The Tsar Bomba is the largest nuclear bomb ever tested.
Four zeros more.
What?
Four orders of magnitude more.
6. Yes. They tested it on Nova Zembla and even the windows broke in Finland. But nobody got killed during this test. But this bomb was more powerful than all weapons that were used in both world wars combined. So it's massive. So theoretically, it's like detonating 6 million nuclear bombs all over the world. Well, that's not entirely true. It's like detonating them at a single spot, and that matters. It's also the same amount of energy that would go in an earthquake with 12.9 on the Richter scale.
Sure.
So the fireball would be 140 kilometers in diameter. If you would see it in the horizon, it would just burn. The crater would first be 110 kilometers in diameter and 36 kilometers deep. Then it would collapse and flatten out to 180 kilometers in diameter and be 1.4 kilometers deep. There would also be a tsunami depending on if it lands in water or and what the depth of the water is. And actually the earthquake that is caused, because there will be an earthquake, is weaker than what I said. It's 10.3. That's because not all the energy ends up in the earthquake. And there would also be an air blast. When you stand away 1,000 kilometers, you would still have a pressure wave of 3 bars. Quite massive. And the melt would be 1 kilometer thick. And I used the impact calculator that's available on the internet for this. Not everything is certain, but close enough for what we know today. So this impact energy and the earthquake energy, only 0.014% of the energy eventually ends up as earthquake. The rest is heat. And that heat ends up inside the earth somewhere. So we're going to look what happens. When an impact happens, well, it basically explodes. Because of the energy, you cannot go anywhere, so it explodes. And this is where melts would form during that impact. And this is a simulation that showed that also deeper there could be probably melt over there or maybe somewhere. I'm not entirely sure where, but even deeper there's also melt happening because of decompression. Now let's take a look at a larger crater. What would go with that? 1,000 kilometer diameter sounds crazy, but we actually find these on the moon. This size of craters, and also on Mars. How do you calculate that? Well, you have the energy involved is a half times the mass times the velocity squared. And the mass is the volume times the density of the impactor. So you can actually calculate how much energy goes in there. And the volume is the diameter and all. This is formula. What you need for such a crater is a meteor diameter of 221 kilometers. Quite large. Then you get an energy amount of energy involved that is 4.12 times 10 to the 26th power joules. It's unimaginable. Basically, we have 3 types of craters that Michael Oort says were involved, and he says there were just a second, there were about 36,000 of these, 100 of these, and probably 1 or 2 of these, but that's maybe none, and we don't know, but statistically there could be a crater of 5,000 kilometer in diameter. But a B crater is 185,000 times more powerful than crater A, and the C crater is 244 times more powerful than crater C, crater B. Michael Oort says, oh yeah, well I said this just now. It's now okay, I'm going to estimate it. I'm going to leave the 2 largest craters out. The rest I'm going to add up. I used Excel for that. That would be 6.7 times 10 to the 28 joules for all the meteorite impacts combined. But I think personally, if you saw my last presentation, that most of the craters happened on one side of the planet, and the other side was relatively intact. Which side would it be? Well, I think the Pacific side, because that is where we find the large basalt plateaus, which we also find on the Moon associated with craters. This would be the impacted side, and this would be the unimpacted side. And basically, before the continents moved, I think it was this that caused basically to destroy the continental crust that used to be all over the Earth, I suppose, and left only a continent over there. That's my idea. So half the crust is gone. Next, how much heat actually is inside the Earth still today? Well, when we take a look, over here we have 20 degrees Celsius, or maybe less now in the winter. But when you dig deep, over here it's already 1600 degrees Celsius. When you go to the core, it reaches over 5000 degrees Celsius. So the inside of the Earth is very hot, and we don't have a problem with that. Heat, you can calculate how much energy is involved in heat using heat capacity of a material. Heat capacity is joules per kilogram times Kelvin. Kelvin is the same as Celsius. Joules is energy, mass is in kilogram, Kelvin temperature. Mass is density times volume, and Kelvin starts at 0, that's why we usually calculate in Kelvin instead of Celsius. It's easier. Iron, yes, heat capacity is a property of a material. So iron has a heat capacity of 450. Water can hold almost 10 times as much heat per kilogram. Granite is a little bit less, and olivine is a bit more. Why these materials? Well, this is inside the Earth's core, this is at the Earth's surface, this is at the Earth's crust, and this is inside the Earth's mantle, mostly. It's a bit of a mixture, but basically this is it. Okay? So, when you want to know the energy, it's the heat capacity times the temperature times the density times the volume. The density of the inside the Earth is also known. This is a graph showing the density. This is the radius of the Earth. So here we have the crust. I shake a little, I always have that. Here's the ocean. Has a density of about 1 kilogram per liter. Inside the Earth, it goes to over 12 inside the core. The temperature is known, so we can actually calculate how much heat is inside the Earth, how much heat energy. I do that by dividing the Earth into shells, because every shell has certain properties, and then add up all these shells together. And I use 1 kilometer thick shells, and I used Excel. This is a volume of a shell, basically the volume of a sphere minus the volume of a sphere that's smaller. And this is, adding it all up, it leaves me with 1.03 times 10 to the 31 joules. This is the heat inside the Earth today, and this is the impact heat of Oort. Could also be 15 or 4, it's an estimation, but this is the idea. And that would mean 6.5% of the heat inside the Earth is, so if we would have the same bombardment as what I described, just now, that's 36,000 meteorites, it would mean the total amount of heat inside the Earth would increase with 6.5%. So it's not obliterating the entire planet whatsoever. So it's not too much heat if there's a reason that the heat ended up inside the Earth instead of on top of it. Okay, so let's take a look. What does heat do, actually? Take a look at this statement we saw before of the critics. Exposure of the mantle, blah blah. Boil the ocean dry. That's the same as saying your oven has enough energy to set your curtains on fire. They are not on fire, so you don't have an oven. Okay, so that's not... okay, and the Tsar bomb released more energy than all weapons in the wars combined, but nobody got killed. So, yeah, you can't say so much energy, so much kills. So there are two important issues. One is the amount of heat, and the other one is the transportation of heat. Where is the heat? Okay, heat transport. How do we get the heat from there to there? Basically. There are three ways to do that. Heat flow, conduction, or thermal radiation. That are the three ways to transport heat. And if none of these is available, the heat stays where it is. That's why the heat is still in the core. Heat flow, it's this going from up to down, moving material that is has a temperature. So this is flow, this is no flow. Yeah. Then conduction is transporting heat by materials that are touching each other. So the pieces of ice in a glass of water is a nice idea. You have cold over there, you have hot over there, it's touching each other, and eventually if you wait long enough, everything will have the medium temperature. That's the second way. This is good conductor, this is a bad conductor. Okay. Here we have thermal radiation, that's shining light, mostly infrared, but also other light into the universe. This is good radiator, and this is bad radiator. That's about it. Okay, now heat, we can trap heat. Let's see how it works. We have a random piece of rock, melt it randomly, see what happens. Well, it expands. Now, assume we have this molten rock that holds more energy than this water can handle. What would happen? So we throw water on it, we would say it evaporates, okay? So this water would start to boil at some point, and the lava would start to cool down. Red is a little bit colder than yellow in this thing. Then the cooler lava would shrink, and it would be deforming a little, and eventually you would get a solidification. You would get a layer on top of the lava, and eventually you will end up with this. Lava that's underneath that crust, and water that is on top of it, not getting that heat that should boil it away. So you can trap heat inside, and the water would not do anything. So for the oceans to evaporate, all the heat must end up in that ocean, which does not happen. Okay, like this. This is an example of very fresh lava that has a molten layer on top. You can just put your foot on there. Don't try this at home, but it can be done without burning your shoes immediately. Yeah. Okay. Then we have my model. What would happen if you would have this catastrophic plate tectonics, and you need to release some things of what John Baumgartner says about this, because he immediately wants this crust to be solid. I think that doesn't make sense, and it is of no use. What would happen if you would separate these continents, say this is Africa, this is America, then you would end up with the Atlantic Ocean eventually, but at first you would have a piece of lava in the middle, which it boils away the ocean there, but it will end up in the colder areas on the continents. Also, because it's more hot, it will expand so it will also push the water on the continent. So this is a bit exaggerated, but this is the idea. So then, basically, the lava has all the freedom to expose all its thermal radiation to the universe, rather than boiling the ocean. Okay. Now let's see what happens. Well, the water will try to gain more land, so it will flow off the continents, enhancing this solidification process. And it will, I said shrinkage cracks. That's a couple of years ago I made these images. I don't no longer believe these are shrinkage cracks, but the rest, okay. When this happens, this water will push it more down. It will push it more inward, and eventually it will press this lava out more and more. And eventually you will end up with two slabs lying on top of each other, and in the middle you would have this closing seam over there. And that's actually what we call the mid-oceanic ridge today. So I think this is what happened. Now we have this situation of dry continents and wet oceans. Okay, now we can calculate how much thermal radiation is involved in this process, assuming that what is now basaltic layer would all have been molten at one day. Okay. For that you need the Stephen-Boltzmann law, and it says radiation is energy times energy divided by time. That is some constant times the emissivity, that's a property of material, times the area, times the temperature to the fourth power. That fourth power makes it very, very strongly non-linear. And that's actually quite interesting, because the answer is in watts, joules per second. That constant is a very small number. For basalt, that emissivity is 0.72. The area is square meters, temperature is in Kelvin. Okay. Now let's assume we have one block, 1 cubic meter of basalt, and it's exposed only on the top for 1 square meter. How long would it take to cool down? Well, it depends on the temperature. If it would cool down from 2000 Kelvin to 1900 Kelvin, it would take about 7 minutes. If it would cool down from 1000 Kelvin to 900 Kelvin, it would take about 2 hours. If it would cool down from 300 Kelvin to 200 Kelvin, it will take 20 days. And from 100 to 0 won't happen, ever. That shows how much non-linear this is. Okay, next one. We have these two blocks. One is larger than the other, they're equally thick, and only exposed on the top. Which of these cools down faster, do you think? Equal. Let's see. We have the volume times density, and etc. Volume is area times thickness, and here we have the area also involved in this answer. So eventually you end up that the area is irrelevant, but only the thickness of this material matters. So indeed they do cool down equally fast. This is probably, maybe it's going too fast for you, but I hope you get the idea.
It likes me to do the calculation, but it makes sense.
Okay. So this is the formula that we are going to use instead of using volumes. Okay. What if the entire ocean crust was molten? Well, then basically the Earth would look something like this. So wet continents and lava all over the place. How long would it take to solidify? Well, I used Excel again to use those formulas. Okay, start temperature 1600 degrees, and it's 7 kilometers thick. And it will end the end temperature there. It will solidify 1000 degrees Celsius. Okay. Then we can fill it all in. Oh yeah, and this is an integrated version of the Stephen-Boltzmann method. Get answers directly. And eventually, I would say that it would take 4 million seconds, which is 1.5 years, for the entire oceanic crust to solidify. So if you would melt the entire oceanic crust all over the world and you would expose it all over the world to the universe, then it would take 1.5 years to solidify. Not billions of years, what you saw in that movie of NASA, not even weeks, weeks, not even thousands of years, no, it's 1.5 years. So that's all this millions of years of lava thing is complete nonsense. Okay, this is not entirely complete because you also have latent heat fusion. That is, when it solidifies, it also adds more energy to this process. So it will take a little bit longer, but we can also calculate that, and it appears that it takes 2.3 years longer. So the total solidification time should be 3.7 years. But this is thermal radiation only. We have also this water coming in, helping the process speeding up a little. It is in the right order of magnitude for the Genesis flood. It may be slightly too long, but not much too long. And who says the earth had to be completely dry for the ark to be open and let the animals out. Okay, after the flood, then conduction took over to get rid of the remaining heat. But that's much slower. We can also calculate that. This is the formula, and it means the thermal conductivity times the area times what the line is called, divided by the thickness is the heat conduction per time. That's a formula to calculate conductivity. And the thickness is important. It's linear. If you have a 1 meter thick wall, it will take 10 times longer than a 10 centimeters thick wall. But eventually, the coldness will go down inside the material still. Now, I did this calculation using Excel again. These represent layers of 50 meters thick, and this represents time. So time steps. Yeah? Okay. The time steps are, I can't remember what it was, I think years or something, but we'll get back to it later, we will see it. Green means about 20 degrees Celsius, yellow is 500 and red is 1000. So at 0 years it is just solidified, but only just. And after 90 years you see that the coldness will also already have gone down several hundreds of meters. And this is after 1,000 years, 2,000 years, 3,000 years, 4,000 years, and 4,500 years, which is about maybe the time that has passed since Noah's Ark was abandoned. Nowadays then the maximum should be about 600 degrees Celsius at 4.7 kilometers deep, after only a couple of thousand years. So if you would take millions of years, the entire oceanic crust would have been very, very, very cold. So this means that volcanic activity cannot last that long. Three random weird phenomena that are involved in the process. You could ask why, how do fish survive? Well, first let's go take a look at the thermocline. If you have hot water which kills off the fish and you have cold water over there, hot water has a low density and cold water has a high density, and actually these two don't mix well. This is known as the thermocline. You cannot get water very deep to be as hot as the top. So fish could just have survived a little bit deeper during this process. Okay, power law creep. This is an important one and a bit hard to understand. But this is the main part of John Baumgartner, his catastrophic plate tectonic theory. If you have a piece of rock and you put a lot of pressure on it, and then you put shear stress on it, so that direction, then you can deform this rock if you put enough pressure on it. But if you put a lot more pressure on it, well, this is not good. Just a second. If you put a lot more pressure on it, it will stress even. It will deform even more. And this process of adding twice as much stress will not make it twice as much deformed. It is very non-linear. And it's so strongly non-linear that this can actually be as viscous as water if you add enough force to it. It's extreme conditions, but then you can make a rock just like water. It's a bit like toothpaste. Toothpaste is actually solid unless you squeeze it. Then it becomes liquid-like. And it reduces 14 orders of magnitude of the viscosity. Crossover depth, that's another weird phenomenon. We are used to magma going up inside the Earth because it has a lower density than the rock surrounding it. But magma appears to be more compressible than solid rock. So if you put enough pressure on the magma, it will actually become smaller than the same solid rock. So if you go deep enough, then magma that won't go up, it will go down. But for that you have to go about 200 kilometers deep or 400 kilometers deep, depending on the rock type. So the crossover depth is about there. Every magma above it will rise, every magma below it will sink. This has been tested in laboratories. So how can we use these things? Well, if we have these large impacts and we have this crossover depth and we have the power law creep, then that means that will result in catastrophic plate tectonics. That's cause and effect. So Michael Orden, John Baumgartner both don't want this, but I think it happens. They don't like each other. Okay, if you have a small impact, 200 meter, if it's smaller than 200 meter meteorite, then you would have this striated crater, molten rock over there. There you see a legend. And then eventually we would end up with a simple crater. This would collapse outward. What we also saw in the previous presentation is that if you have a larger crater, smaller than 200 kilometers, you will end up with a crater with this dome in the middle, central uplift. So it will collapse outward and upward. If you would go even larger, then part of the melt, I'm not sure about this, but if this doesn't work, then just make this one larger. Then part of the melt would end up below this crossover depth. Okay, and then something interesting would happen, because this melt would want to go up, but this one would want to go down. And if that happens, then you would end up with a really weird deformed crater and a heat sink, and eventually end up with a large, what they call a large igneous province, a layer on top, and a big melt blob underneath it, and something that goes all the way down to the core. And I would say this is an explanation for hotspots that work better than what scientists used to say. And this is basically what happens, strange deformation. Okay, now if we would have an even larger impact, then the majority of the melt would end up below in the crossover depth. And then basically, well, almost all will go down and will collapse inward and cause a mountain area there. But I wasn't just talking about a single crater, I was talking about a bombardment. What if we would have a complete bombardment here and one large crater on the edge of the bombardment? What would happen? Now, I think here would be the water, not there. So this would solidify faster than that side. And eventually you would have heavy here, lighter here, and this is medium. This is the heaviest part, so it will sink down and collapse that way. And then eventually it would look like this. And I think this is an explanation for a subduction area. So instead of something solid going inside the Earth, it's something liquid going inside the Earth. But then we have also this large impacts that with a bombardment on both sides. Then you would have the same principle, except that you would have a very liquid shape, turning up more symmetrical, something like this, and it would just collapse inward and downward. And my conclusion about this part is that the larger the impact, the more the heat tends to end up inside the Earth rather than on top of it. Okay, if you would have two sides, the Earth is a sphere, but you can also represent it as flat, you would have this bombardment on one side, then that would mean this would collapse outward, inward for the crater, but outward for here, and then there would be stress over here, causing this to rupture and get away from each other. So I think this is an explanation why continents moved because of impacts. And eventually it would fill up from, it's 3D, and the result is what we saw earlier. So we have the 7 types of what could happen, and this is more to scale relative to each other. Okay, let's take a look. We have these large and simple craters. Well, we have found them. The large igneous provinces, these are all the hotspots we find on Earth. They try to explain it with volcanism going up. I explained it with volcanism going down. Interesting one is Iceland, for example. You know, this very large igneous province, that this Iceland itself is an igneous province with a hotspot beneath it. And some of these that are large enough reach all the way down to the core. This is Afar, this is one in the Pacific. And hotspots in large igneous provinces are very much associated with each other. Mostly lying on top like these two. But some are very much displaced. We have a large igneous province over here with no hotspot, and we have a hotspot over here with no large igneous province. What we also have over there, very near, is something that is looks like a crater, but it's not yet recognized as such. It's half a crater, it's near India, it's called the Shiva crater. And some people say to recognize also half a crater near Madagascar, over there. So that's a crater split in half. With the large igneous province over there and a hotspot over there. So if you would combine all these details, you would say one impact causing all these 3 features. Large igneous province, hotspot and a crater. Okay, next one is the orogenies, that's mountain areas. That's this one that I showed for the collapse inward. Maybe the Himalayas. Is this a crater rim? And is this the cause why India even moved? I'm not entirely sure, but I would say this is very much, having a round edge. I'm open to debate about this later.
The sedimentary rocks in the Himalayas, which also, like the Firafort, pre-existed before they formed.
Okay.
If you understand what I'm saying.
Yes, I understand.
It's not a crust per se. It already contains sedimentary rocks.
Okay, I didn't know. Subduction areas, well, this is what usually they say about subduction areas. Plates diving underneath each other. And we find them all around the Pacific area. So I would say this is the bombarded area and this is the edge of the bombarded area. We also find 90% of the volcanic activity of the world there. Convergent plate boundaries. I think when this happens it would behave liquid-like. What I mean with that, well, take a look at this one. It's a spiral shape. And if you compare the spiral shape to what we see with the weather, you see that's caused by what's called Coriolis effect. The spiral shapes you're used to when you look at weather maps. You see some more of these. These are the clear ones, but there's also one that's open to be debated. But in order for these spirals to form, I say it must have been liquid. I think it's very unlikely for solid rock to form spirals. Okay. Continental rupture, well, we have that. Said that already. This is an example where it's exaggerated for this mid-oceanic ridge and the continents on each side. But these things are all over the world. When scientists show the map of Pangaea moving away from each other, they show this. But I think it looked more like this. So it's wet continents and lava all over the place. So this is the reason why everything got underwater. And there would be lava flowing from there to fill up this gap. And when we're in a later stage, and there would also be lava flowing from here between this gap. If we zoom in on that, then we have the Scotia plates, which is a bit hard to explain for most people. But if it is a lava flow, it makes perfect sense to me. I don't know how about you, but to me it makes sense. So then we reach to the conclusion, all flood models have a lot of heat involved. The impacts caused about 6.5%, make it 50, make it 4 of the heat inside the Earth. The distribution has never been examined in detail, and impact heat caused melt below the crossover depth. Heat below the crossover depth caused fast runaways. There is subduction, that's the sinking of the material. The shape of the oceanic crust and hotspots can best be explained by large impacts. And thermal radiation cooled down time of the oceanic crust is in the right order of magnitude for the Genesis flood. The melt caused this continent to become flooded for about a year. The conduction cool-down time calculation of the Earth's crust shows that volcanic activity cannot be much older than several thousand years. And well, this is about the end of my presentation, depending on how much time I have left. Yeah, I think I spent 40 minutes, so we have 20 minutes left. We can also pick a subject we still want to discuss. I have evidence for this, hot drilling projects reaching hot. Why does the moon look different shapes? Flaws in the old Earth interpretation, unsolved issues. So there's also still the issues that I don't know answers about. And how does the heat model fit the biblical story?
Where's the ark in all of this?
Yeah. Well, the ark was somewhere on the water.
Just above the continents, probably.
Yes, on the continents, yes.
So how much water, I mean, the fact that the water will be vaporizing and then raining again,
Yeah.
That'll use a lot of energy out of the system, wouldn't it?
What do you mean?
Let's say the
Yeah.
ocean,
Then condenses, doesn't it mean take heat out?
Yes, it takes. It means you're taking heat out, but it's also thermal radiation that's going to. When water is 100 degrees Celsius, then it goes to be evaporated. It has to cool down only a couple of degrees Celsius to rain back again, I suppose. Eventually, if there's a lot of moisture in the atmosphere. But yeah, it's an issue that must be.
yeah, so that I've seen in the calculations, I understand, and in the conclusion I liked it, that it says it takes just over a year, 1.4 whatever years.
1.5 years, yes.
1.5 years, whatever, for the whole crust to solidify. If the whole crust was magma, but did that take the evaporation, or the evaporation and the cooling down of the water into account? Because that'll use a lot of energy.
Use energy to cool down the water.
Yes, so it's the magma would cool
Yeah.
down faster, obviously, due to the contact with the water.
Yes. And when that water contacts it on the edge, then it will cause steam there. but other places it won't. Yeah, I still don't understand your question, I suppose.
So the Atlantic Ocean,
Yeah,
let's say catastrophic plate tectonics, right? Let's say the continents moved out.
yeah,
So you've got a huge amount of magma that gets into contact with water very quickly.
yes,
So there will be a quick cooling down of the magma there, and a large amount of energy will go into the evaporation and then
Yes.
the rain again.
Yes.
To the water cycle.
yes. But I think that alone would not be enough to cool down the crust. It would, but the thermal radiation is a faster way of doing it. But I think the water will enhance this cooling process.
Yes, but I think there's anything that I maybe missed in the calculations is the effect of the water cycle.
Yeah, I haven't calculated that exactly, because for that you need to know how much water gets into contact with.
Sure.
And I think you would need to simulate that rather than calculate it. So,
I have a question about this in relation to your previous talk, in which you talked about the impacts on the moon.
yeah,
And you're saying, yeah, the lava flows back into the older craters, etc.
yeah,
But it takes quite a while, compared to the length of a flood year, to solidify the lava or the magma. So any new impacts will be impacts on liquid lava, right? On the moon.
most of them in the first time of the flood, yes.
So would it really leave visible craters now?
On the oceanic crust. On the oceanic crust, no, I suppose
On the
not.
moon?
On the moon, on the moon there's a lot less energy involved, because an impact on Earth causes it to be much more powerful because of the gravity of the Earth. Eventually the crater size would be just the same, but also because it takes less energy to make a crater on the moon. So the amount of heat involved in the Earth is a lot more than on the moon. So I think on the moon it solidified a bit faster, but also there you saw only a few craters that happened after the impacts craters solidified.
But many of the smaller craters, they happened within the previous larger craters, like a small footprint in a large footprint.
Yeah,
So that means that the lava of the old big crater must already have solidified.
yeah,
And this must happen within the flood year, because it's the same bombardment as the one on Earth during the flood.
yeah, but maybe in the first 4 weeks whatsoever. I don't know, but that's you're right. That's still part that we need to investigate. Yeah,
But both of these models support that the average temperature of the seawater will rise.
yeah,
And so that will enhance so the whole idea of having a sudden ice age looks inevitable in both models, whether you've got an impact or a catastrophic plate tectonics, am I right?
yeah. I think I don't know enough about these things to be sure, but I think this would mess up enough to cause also rain to fall on the poles a lot, and there it would cool down a bit faster than anywhere else, so it would cause an ice age, I think. But this is a simplistic answer from somebody who doesn't know enough about it. Yeah.
Have you excluded completely the possibility that meteorites that hit Moon, Mars, Earth could have happened only in one time space? So is I'm kind of hearing that this happened at or near the same time.
Yes.
Have you excluded the possibility that it could be different?
Have you seen my previous presentation?
You did not say this
Yeah.
happened at the same time, but
Yeah.
I've heard an implication.
Yeah, the
So I was
evidence
just
on the
trying to
moon,
say,
the
did you-
evidence on the moon seems to show that at least the majority of the craters happened within a short time span.
Yeah.
because they all seem to be related, or in,
So my question is very specific. Have you excluded completely the possibility that this could not have happened at the same time?
I would say for some of these craters, yes, but
On Earth
otherwise,
now, so I'm trying to track it down into this conversation. Right?
yeah. Well,
So-
I would say technically I cannot exclude the possibility that there would have been multiple events of impact. But if there were multiple events, then every time there were multiple meteorites involved. So it was never an isolated impact. They are all always combined.
Okay, so it is possible that there could have been thousands of years, meteorites, thousands of years, meteorites, or hundreds of years.
Theoretically, it could be, yes. Some people say that that this is too much impact for the flood, like Danny Faulkner says. Most of the impact did not happen on Earth, but everywhere else, and the majority happened during the creation week.
Okay,
I
so, okay, that's
don't know.
helpful. That's
Yeah.
helpful. No, you're not making a major statement that all of this happened during the flood.
I think that is the most likely explanation,
Yeah,
but
but
I
it's
can't
not-
say more than that.
Okay, good.
Sorry, Dr. Brown's hydroplate theory, what do you think about that? Do you agree with it or you disagree?
Well, I can tell that now, I suppose. But yeah, I still have 10 minutes. In my next presentation, I will also go on the hydroplate theory. The hydroplate theory assumes that there was water trapped underneath the continental crust, squirting out like huge fountains, and then drifting on top of that water. There are a couple of problems I have with that, but the most obvious problem with it is that for that you need a very flat bottom of the continental plates. You need a flat bottom to float on top of a layer of water. But they are not, they are very bumpy. So continents moving on water, for that there is evidence that the shape of the continental crust is not right. So the movement appears to involve also deformation of the of rock, deformation. So and for that to happen, John Baumgartner has currently the best model because he understands how rocks work. And John Brown doesn't. Walt Brown doesn't know that. He has been involved in the flood science review. A couple of flood models were involved in that, and he didn't have answers to that type of questions. Yeah.
John Baumgartner has his computer simulation is done. He divided the Earth in small squares and he used the conservation of mass and momentum.
Yeah.
And so he simulated the whole event and with all of the laws that's applicable. And you didn't have that same level of research in the hydroplate theory. It's not even, I don't even think it's just past an idea. It's not even a hypothesis in my opinion.
Somewhere in your presentation you hypothesized the possible explanation for the origin of the mid-oceanic ridge
Yes.
in the Atlantic.
Yes.
But to quote Walt Brown, literally, I think, the oceanic ridge wraps around the world like a seam on a
Yes.
baseball. It's everywhere.
Yes.
Well, not only in the Atlantic. So can
Yes,
you
it's
explain that
correct.
as well?
For that I need a map. It will be in my next presentation, but I won't go into detail about that single image, so I can do that now. Just a second. Over here. Over here you have a map of the entire oceanic crust. Just, why don't I see anything?
Yeah.
And then you see this mid-oceanic ridge over here, which is water flowing from there and water flowing from there. Over here you see it, you also see this, but of course you would have water flowing from the continents on all the oceanic crust. But when you look at this, you see this thing has been pushed more towards America than towards Asia. Also this one. I think that has something to do because there is a mountain range over here, which isn't at the other side. It's also not here. So the mountain range would block the water to flow that direction, causing more water to flow from here than from here. So that's what pushed it away over there. It's an idea I have, and yeah, it needs to be simulated to test if this is possible. So I wouldn't say it's all worked out, but this is my idea.
It's worked out in your mind.
What?
It's worked out in your mind quite correctly.
Okay. More questions?
I just want to add a comment I read yesterday during my preparation on the Vredefort Dome. I had a book that I referenced some of the evidences, and some of the earlier geologists actually draw a link between the Vredefort Dome impact event and the Bushveld Igneous Complex in South Africa. That was also, I think, in the 1920s, due to some evidences. I forgot what it was, but it's worth having a look because you draw the parallel between the impact events and the igneous provinces that you mentioned.
Yeah.
I must actually find the pages and just send you
But for the
copies.
Vredefort Dome, I suppose there would be a very small, small igneous province.
Yeah.
Because the impact is relatively small to what I would expect to cause
Yes.
it. It's just below the just above the threshold to form a real hotspot.
Mm.
I
And
think.
in terms of uniformitarian ages, the two are quite similar, the age dating of the two,
Okay,
the Bushveld complex and the Vredefort event.
okay, that's interesting.
Interesting, very interesting.
Yeah. Okay. I have done this quicker than I expected. Do we want one of these 5 subjects?
When is it coffee?
I also wanted to ask, was it good?
This engine runs on coffee.
3 minutes. You can also have coffee if you want. Thank you.
Thank you.